There you go. Here we are at our first example. And so we have this nice fraction here of x cubed minus x minus 4 all over 2x squared. Now, to solve for this, I would like to employ a nice strategy, if you will, about how to deal with these kinds of problems. When you have a fraction, we need to compare which side has the larger exponent. And so in this case, because the numerator has the larger exponent, or the better term is degree, well, then our strat will dictate that when you have the numerator with the larger degree, what we need to do is that we will divide by the denominator. Now, you might be asking, how in the world do we divide that? It's a fraction. Of course you will be dividing. It is a fraction. What we need to do here is that we need to go back to the back of our heads, and remember we have our good friend distributive property. Oh, hopefully we still have that one. We can easily distribute this across the numerator in the different terms with that 2x squared. And so we will look like something along the lines of this. We will still keep our integral, but now we are going to distribute across each term in the numerator. X cubed over 2x squared minus x over 2x squared minus 4 over 2x squared dx. Now, for each of these, thankfully, there will be something that we can simplify with to make our lives easier. So, starting with the first term, we will begin with x cubed over 2x squared, simplifying to x over a whole 2. Then, by subtracting the next term, with x only to the first power, it's going to be 1 over 2x in that spot. And lastly, with the 4 over 2x squared, all we can really factor out is a whole 2, leaving us a 2 over x squared dx. Now we have three separate parts here which need our attention. We have x over 2, negative 1 over 2x, and a negative 2 over x squared. Now, with enough of our information here, it should be pretty simple that x over 2 is going to be exponent rule, and similarly with 2 over x squared also becoming exponent rule. Of course, because x squared in the bottom is enough to make sure that that rule takes place. Now that 1 minus 2x, that is the key. This is where we will go and use the natural log rule, abbreviated NL for space. And so we now can split this up with addition rule, and it will look something like this. It will be x over 2 dx, and then subtracted by the integral of 1 over 2x dx, and then subtracted by 2 over x squared dx. We have these three different terms, and again, each of them we've already explained which part we will use for them. So starting with the x over 2, that will simply turn into x squared over 2, but then we just remember that that new exponent will give us another 2 in the denominator, subtracted by 1 over 2x. So remember that we can leave that coefficient outside and do natural log of x in the absolute value as stated with our rule. And then lastly, with the 2 over x squared, we will actually result this in an x to the negative 1 power, because we're adding 1 from the negative 2 power. And then we will still keep that coefficient there. And now we need just a plus sign to cancel out with that negative. Pretty good. And then we will add a plus c at the end there. So it looks like all we need to do are some last simplifications, and everything will look pretty good for us. X squared over 4 this time minus 1/2 natural log of x, and then we'll add a 2 over x plus c. Looks like this is the result of our work there. And of course, the last thing we need to do is always to check our work. How do we know that this line of an answer is actually correct for us? Glad that you asked. So our check will turn something like this. We need to go and take the derivative in respect to x for all of this. Back to our check is that we bring down the 2 with power rule for the x squared over 4. It becomes x over 4. We need to subtract by the 1/2 will stay. The natural log of x will go backwards into another 1 over x. And lastly, the 2 over x. Now, this one's going to be a little bit tricky. Remember that 2 over x is 2x to the negative 1 power. So by bringing this negative 1 down from the power rule, all that it will do is make it a negative 2 with an x to the negative 2 power. And of course, the plus c will go to 0. Does this match what we started out with? And of course, if we just do a little bit of factoring, changing that 2 back to a 1 on the top and 2 on the bottom, that does match. Negative 1 over 2x and negative 2 over x to the negative 2 power does indeed match that x squared in the denominator. That all checks out, and it looks like we've actually solved our first problem using multiple rules for the same integral. Oh yes! Looks like we have an example waiting for us again. This time it will be the integral of z over 1 minus 4z squared dz. Now, although we've changed the variable, it should make no difference for our problem solving. But something that I've seen in the past is that my students will take one look at this problem and say,
"Oh wow, look at that. This is just in the denominator. We'll just throw it down there and we'll call it a day. We'll take the natural log of the absolute value of 1 minus 4z squared plus c, and we're good. And then we'll just go home and we'll call it a day."
No, absolutely not. This is going to be very clearly wrong. And why is that? Well, something that I've always said about the best part of integration is that we can check our work. With every single result from our integration, we can actually make sure that it matches straight up. Check. Check. Who would ever want to check? Well, unfortunately, that's the way that we do things around here. So let's have a look here then. If we were to take all of this and take the derivative in respect to our variable z, there should be nothing wrong with this answer. So why don't we go ahead and do that? We will indeed end up with 1 minus 4z squared in the denominator from the check, but I believe we're forgetting something. If only we can rack our brains into remembering, oh yes, of course, the chain rule. Oh man, this is bringing back painful memories, isn't it? We need this, the new denominator that came out of the derivative, and we need to take its derivative as well. Because we started with the natural log on the outside, we need to take the derivative of the inside. 1 minus 4z squared. But would you look at that we will end up with a different coefficient instead of the one that we want as negative 8z, all thanks to power rule. Oh dear, it looks like we were a little bit off. Negative 8z over 1 minus 4z squared does not match up with what we started with.
Now what shall we do?
We will need to do this again, but with a little bit of a modification. Thankfully, this hastily made answer is not all lost. All we need, it looks like, is just to get rid of that negative 8 coefficient. Coefficient? If there was only the very first rule in integration for us to deal with that. Oh dear. And what would you know? That by getting rid of the negative 8 to match that first z, it looks like we will need to have a coefficient of negative 1 over 8 and then take part in the rest of the same integration of the natural log of 1 minus 4z squared plus c. And with this, we should be able to check that. It's quite simple. We've actually done the work for the most part. Coefficient rule once again states that even though we take this derivative, is that we can leave that negative 1 over 8 on the outside, and we end up with the same exact differentiation that we've done earlier with the second parentheses to show the difference. Well, would you look at that? This negative 8 will indeed cancel with that negative 1 over 8. And so, by removing those two, we will end up with just z over 1 minus 4z squared. This does indeed match up 100% of the way through and through the start of the integration.
Victory.
And so, would you look at that? This is how you solve for the integral by, even though you've kind of jumped the gun with running through what you think is the easiest, all we need to do is just to make sure that the check comes through. We can tweak it a little thanks to the rules that we've learned so far, and to come up with the actual correct answer that will not lose us points on the test. And so, with that, this should conclude our fourth rule for integration. We'll be back next time with some trig rules, and hopefully we can work from there to learning the rest of how integration works.